Okay, hey guys, I hope you all can hear me. Yeah, just write down if you can hear me, then we can start. I'm audible, right? I should be. Just to make sure, drop a quick yes or no if you can hear me. Drop a quick yes or no in the chat so that I can know. I can see some of you are there, so just drop a quick yes or no if you can hear me. So anyway, it can be some issue of the chat also. But anyway, this is what we are going to cover today. Sieve of, yeah, okay. Thank you, Nidhi. So we are going to cover Sieve of Eratosthenes. Eratosthenes. We are going to see what is the idea and what can be the easier ways of doing the same kind of task, and what can be an easy way of implementing the Sieve of Eratosthenes, and what can be the associated problems that we can solve using this technique. We are going to see these things primarily. Okay. So first of all, the kind of problem that it primarily solves is basically primality test. And this is a problem which you might have covered right from the time when you have started programming, that how to find whether a number is prime or not. There's a basic problem, or one of the few problems that you learn or you start implementing when you start knowing about loops, arrays, and everything. This is just another version of primality test. So let us first shortly analyze and brief upon what are the different primality tests. We say that a number is prime, n is prime, if for all I in the range 2 to n minus 1, n mod I is not equal to 0. So if n is not divisible by any number which lies between n and n minus 1, or from from 2 to n minus 1, then we say that n is basically divisible by only two factors, 1 and itself, and hence we say that n is prime. And we have also known, using our analysis, using our experiences, that we can say that this range can be converted to 2 to n by 2 as well. We can say that up to n by 2, if we check all the numbers, some or the other factor, if n is composite, then some or the other factor should stay within this range. And what is the idea? The idea simply is that your lowest factor is definitely going to be 2. It is going to be greater than equal to 2. So you're not missing out on the left side. It is going to be greater than equal to 2. And if there is some factor of n which is greater than equal to 2, which is maybe anything, you can say if some factor is greater than equal to 2, suppose some factor f is greater than equal to 2, then you can say n by f is going to be less than n by 2. So you can say, okay, the other factor is going to lie in this range. One factor can be very large, but if I know that a number is not prime, I can ensure that, okay, it lies in this range. So only by checking from 2 to n by 2, we can understand whether the number is prime or not. If we see that all the numbers are sort of co-prime with this number. What is co-prime? Co-prime means that the greatest common divisor of I and n is equal to, or basically is not equal to 0. This means that it is co-prime. So if I see that all the numbers from 2 to n by 2 are co-prime with n, that means that n is prime. We know these things. And the best thing, which is most frequently applied, is that if all the numbers from 2 to square root of n are co-prime with n, then we say that n is a prime number. What we say is that one of these should be a factor, and not only co-prime, we also say that it has to be divisible. So n mod, or say we can actually say the same thing, co-prime as well. But anyway, let us take this. For all I in this range, n mod I should not be equal to 0, then we can say that n is prime. If n is greater than or equal to 2, and we know that this kind of a relation holds, then we know that n is prime. Makes sense? So what is this sign that I've given? This is for all. This inverted A actually means for all. For all values of I in this range, it will be, we have to check this condition. If this condition holds, if this condition not equal to 0 holds for all the values of I, then we know it is going to be a prime number. What is the time complexity? What is the time complexity of this approach? It is nothing but log n. What is the proof? What is the guarantee that always our first prime number, or rather our first factor is going to lie somewhere in this range? We can say, suppose that n is not prime. N is not prime means it is a multiplication of a and b, where a and b both are not equal to 0, a not equal to 1, b not equal to 1. We can say both are greater than 1, thereby we can say both are greater than 1. This kind of a product is possible, and hence we can say that if they are all greater, and if I assume that both are greater than, since both are greater than 1, in order to not fall in this range, both have to be greater than square root of n. So if I say a and b both are greater than square root of n, what can I say? A n is going to be greater than square root of n multiplied by square root of n, if both a and b are greater than square root of n. So I can say that n is greater than n, which is not possible. So this particular thing is not possible. We can say it from here. So this is actually the proof that always one or the other factor is going to lie in this particular range, because if there is one factor which is greater than square root of n, the other factor, which is n divided by that factor, must be less than or equal to square root of n. Make sense up to here? So this is the basic primality test that we always apply. Now what can we say? What is the complexity of this approach? This approach actually takes steps from 2 to square root of n, which is log of n to the base 2. I'm sorry. This actually takes root of n. So this is going to be the approach. So this one is not possible. So we can say that is order root of n. Root of n steps are required. We can say that this algorithm will run for order root n time. Now suppose we change the question, and what I require from you is, due to some other question, I want you to solve this, that find all the numbers, all prime numbers up to n, up to a certain n, which can be as large as something like this, 10 to the power 6 or 5 in 10 to the power 6. I want you to find all the prime numbers up to this n. What shall we be doing following this approach? हम कुछ ऐसा करेंगे. We can say that from 2 to n, or maybe for all the odd numbers we'll be doing. Even numbers we know they cannot be prime. So 2 is a prime number, and then from 3 to 10 to the power 6, all the odd numbers we can check whether they are prime or not. So if they're divisible by 3, very easily they will escape. But on an average, we can say that the algorithm climbs up to n to the power n into root n. Why will this be the case? Because in case of n equal to 2, we will have something like 2 root 2, we'll have 3 root 3, we'll have 4 root 4, 4 root 4, So for n equals to 2, we will have only root 2. This is the time taken, order root n, and then we will have root 3, and we will have up to root n. So we can say that there are about n terms, there are around n minus 1 terms, and we will hence have somewhere around n to the power root n order. This is an approximation, and the problem is that over here we can see that it is clearly falling outside the bearable limit. We can see that 10 to the power 6 means n root n goes to 10 to the power 9. but we can run only about 10 to the power 8 operations or 2 into 10 to the power 8 operations per second. We cannot definitely spend so much time behind finding all the primes. We just require all the prime numbers. And if you say that, okay, I'll be dealing with only the odd numbers, it will only reduce this by a factor of 2. That is not sufficient, because it may happen that after finding the prime numbers I have to do many more things. So I just want the prime numbers from you, and maybe after that I have many more operations. So definitely I want you to complete this positively within 10 to the power 8 operations, or at least within 1.5 into 10 to the power 8, 2 into 10 to the power 8, something like this. So can you understand in what case our trivial primality test is failing? So basically when we have to find for all the numbers, that is basically the stage where we are failing. But we can see, suppose we have got something like this. Suppose 37 square. 37 square, it has got some value, we can find out. 37 square, if suppose some n is equal to 13, or suppose m is equal to 37 square, and n is greater than this. So we are somewhere encountering this value. What can we say? That in order to prove that it is not a prime, we have to travel up to 37. 1, 2, 3, 4, up to 37. So 37 steps are required. Similarly, we can say that for some number like 137 might be a prime. Okay, I'm assuming that this is a prime, or maybe a prime of 3 digits. So when we take that kind of a prime, we require to go for 137 steps in order to find out that this number is not important for me, right? So, or rather this number is not a prime. I have to cover 137 steps. And the problem that we observe through this approach is, we know we have to go up to n. So when we know that 137 is a prime number, why are we looking at the multiples of 137? For 137 we have done the checking, that's fine. Now why are we looking at the multiples of 137? If we could have somewhere, just for 137, if we could have done something like this, that for 137 mark all its multiples, which are 260, 274, 274, and then we have again 137, which is 400, 411 I think, and all these numbers if we can mark up to what number? Up to 10 to the power 6. We can say directly that all of them will be prevented from being rechecked time and again. We can easily prevent them. And what can I ensure? That if I travel from 137 to all its multiples, I will be visiting those numbers some point of time or the other, right? कभी ना कभी मैं तो, अगर अभी मैं उसको मार्क नहीं करूंगा, कभी तो मैं इसको विजिट करूंगा, उसके पीछे तो मुझे टाइम देना पड़ेगा. बट अभी क्या हो रहा है, 137 रिक्वायर्स टू स्पेंड ओनली वन इंस्टेंट ऑफ टाइम विद ऑल इट्स मल्टीपल्स. वो अपने हर एक मल्टीपल को जाके बोल रहा है इसको मार्क कर दो और खत्म करो इसका कहानी. The moment it marks it, the next time when this when the control will reach I equals to 274, what we can ensure is कि वो extra computation नहीं होगा, या फिर 137 square. इस केस में 137 extra steps नहीं होगा, इस केस में 2 या 3 steps जो भी involved नहीं होगा. We can ensure all these things, and hence the idea that we will start marking the multiples in order to bring down this n root n. Okay. So that's it. This is basically the idea. और इससे हम क्या कह सकते हैं कि अगर अब expand अगर करें तो total idea क्या है? When you have numbers like this, when you have number like this 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, and up to 25 I'll be doing this, 21, 22, 23, 24, 25. Whenever we see 2, what we can say is that 2 is a prime number. Take 2 over here with you. We have taken 2. And now we will say whatever are multiples of 2, just throw them out of the journey. So you have thrown out 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Then we will say that now we have come to 3. We know 3 hasn't been marked by the previous prime numbers. So 3 is not a multiple of the prime numbers you have seen so far. Now this is the idea. You can directly use it to say that okay, 3, that means it is a prime number because it is not divisible by any other prime number before it. and it is greater than 1. So this is a prime number. So we take this as a prime number, and we will say when it is a prime number, mark all your multiples. So we can say that we'll be marking this. It is already marked, 6 is already marked. We'll be marking this 9, and then 12 is marked, then 15, and then 18 is marked, then 21, and then 24. Yeah. So we'll be marking all of them. We'll be traveling through all the multiples and we'll be marking all of them. Makes sense till now? Cool. There is one thing which we should remember at this point of time, and that is marking all these multiples. How much time is involved? For marking all the multiples of 2, how much time is involved? It is n by 2. For marking all the multiples of 3, how much time is involved? Somewhere around n by 3. And similarly of n by 4 and so on up to n. So you go from 1 plus up to n you go. If you have to mark for all the values, right? If for all the values you say I'll be marking my multiples, you basically won't have this plus 1 factor. You'll be having only from n by 2 up to n. And we know that if we add it from 1 up to n, 1 plus, I think something like this, you can do something like this, n by 1 plus n by 2 plus dot 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 up to n by n. This is basically called the harmonic mean of n, or the nth harmonic number. This is basically the nth harmonic number, and we say that this falls somewhere in the range of around ln n to ln n plus 1. So what we can say is, just a second, it will take us from n ln n to n ln n, just a second. Ln n is, okay, no, it's 1 plus 1 by 2, yeah, it goes from n ln n to n ln n plus n, something like this, okay. So basically if you take the values 1 plus 1 by 2 plus 1 by 3 and dot 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 up to 1 by n, you will get harmonic mean. So you have this kind of a relation, 1 plus 1 by 2 plus 1 by 3 up to 1 by n, you will have the harmonic nth harmonic number. So forget this relation. This value lies in this range ln n to ln n plus 1. So from here you can actually derive this, that if this sum lies in this particular range, then what will this sum lie in? This will easily lie in n ln n to n ln n plus n. So up to now we know whatever operation we are discussing that we will be doing, that will not take time greater than n log n. So this is first of all an upper bound which will work. We don't know if it is a strict upper bound. I'm not saying that this will be the time complexity. What I'm just saying is that the operations you have done till now is going to stay below n log n. And you know that the method which we are comparing our algorithm against, which is the basic method of primality, that check for all the numbers whether that is prime or not, that is n root n. So theoretically, practically, however you see, till now whatever work we have done which is repeating for all the multiples, for all the values, that is definitely some way better than what we have over there. So if you have to follow the naive algorithm, that is for every number we'll check whether that number is prime or not, we have n root n, and just a simple deviation from that, we will now say that for all the numbers we are going to mark their multiples, or for all the prime numbers we are going to mark all their multiples. What is the idea behind this? That any number which is a composite number will be divisible by some prime number before it. कोई भी number जो कि composite होगा, that will be divisible by some prime number which occurs before it, and this is only the idea that we are using over here. Make sense? So yeah, now what can we say? Now we can say something like this, that let us see, do we need to check, okay, 3 we have got as a prime. Why? Because 3 is not divisible, 3 has not been crossed out by anyone in before it. So we can say 3 is a prime number. Now 4 has been crossed out. We can have a flag for all these elements, and every flag at every index is going to tell me that whether that element has been crossed out or not by any prime before it. So we can see that 4 has been crossed out. So what will we say? 4 is divisible by a prime. Now think about it. Should we use 4 to cross out its multiples? Should we use 4 to cross out its multiples? the way we have crossed out the multiples of 2 and 3, should we use 4? The answer is not required. Why? Because we know that 4 is a composite number. Now, whenever you have a composite number, it must be divisible by some prime number which is less than it. So for that prime number, definitely you have crossed out all the multiples of that prime number. And all the multiples of this number, this composite number, is definitely going to be all the multiples of its factors. So this 4 over here is divisible by 2. So if we say that we have cancelled out all the multiples of 2, can we say that we have also successfully cancelled out all the multiples of 4? And exactly, that is exactly what is happening. We have cancelled out all these factors, all these multiples of 4. We have crossed out 8, 12 and 16. Now let us move to 5. We will say that 5 hasn't been crossed out. 5 hasn't been crossed out. This indicates that before 5, there was no prime number which divided 5. That was the reason no prime number could actually cross out 5. And hence we say that, okay, we can add 5 to this list of prime numbers, because since it has not been crossed out, it is guaranteed to be a prime number itself. And we will say that now rush out, like move out and cross out all your primes. Whatever you are dividing, cross out all your multiples. So since 5 is a prime number, we will say that now enter the field and cross out all your multiples. 5 will go and see 10, 15 and all these are marked. 25 is not marked, it is going to mark it away. That's basically the journey. So in this way we can say 5 has been added. We'll come to 6. We see that 6 is marked. Again we can say 6 is marked means 6 apna composite hai. Some prime number has said that he is my multiple. That is why 6 has been marked. So what can we say? That if I go to mark my multiples of 6, I will find that all of them are marked. Why? Some or the other element, some or the other prime before me has marked all my multiples. Why? Because I am divisible by 2, I am divisible by 3. Whatever are my multiples, they are all divisible by 2 and 3. So 2 and 3 I have definitely crossed them, so I don't need to roam from here. So we can say that in this way, we can carry our journey forward. We will say that 7 has not been marked. So we will include 7 over here and we can cross out any multiples of 7. Then we talk about 8. 8 has been marked. That means it has been taken by some prime number. We will not add it. 9 has been marked. 10 has been marked. 11 has not been marked. And in this way, I'm going to get all the prime numbers now. 13, 17, 19, 23. 13, 17, 19, 23. I'm going to get all of them. So what are we observing over here? For all the prime numbers, we are saying that do this kind of an operation. Go up to n through your multiples. Follow your multiples and reach up to n. And see what are the elements you can cross. So there you go. You can actually find out something like this. Yeah. You can see that for 2, we will require to visit at most these many integers. Why? Because n by 2 is actually the number of multiples of 2 less than equal to n. Always, this is a standard formula if any of you are not aware of it. N by I is equal to the number of number of multiples of I up to n, number of positive multiples. So it starts from I itself, I, 2i, 3i, it will go up to some value which will be less than equal to n. You can say that you can represent that number by n by I. And I showed that in the worst case, we will have all our primes, that is from all the values, will be visiting all their multiples, then it will be limited by n log n, which is also good enough. But our observation is that all are not primes, and if it is not a prime, we do not need to visit its multiples. The simple reason being that we are visiting the multiples in order to identify them as composite. Now, if we are saying that this is a composite number which is something like p1 into p2 or p1 to the power something into p2 to the power something, this is a composite number, we will say all its multiples, they are already divisible by p1. So p1 had only crossed it for the first time because it is p1's multiple. So we don't need to visit it. That is the reason we said that first write down all of this, maintain an array where every position is going to store either it is marked or is it unmarked. And then iterate it from 2. From 2 you are going to iterate it, whatever is unmarked, you will add them to the list of primes, and simultaneously after adding to the list of primes, you are going to say that now follow me to the multiples, all my multiples, and mark them as marked. After that, what you do is that, okay, I have marked it, now start from the next value. So it will go exactly something like that. So this is basically what is a sieve of Eratosthenes, and we'll be covering the applications of this, the varied applications. But before that, any questions? Any questions, any comments, anything that you have got to ask? Any part that you want me to repeat? Okay, so the time complexity, it turns out that the moment we reduce the possibilities, the moment we say that all our prime numbers, all the numbers are not required to visit the multiples, we can say the time complexity can be reduced below this. We can easily reduce our time complexity below this, and we can say we will get something in order n log of log n. So what are we doing? First of all, we are totally eradicating this root n kind of traversal. We are saying that now no longer you need to traverse up to root n in order to find whether it's prime or not. If it is not marked, then it is prime. If it is not marked, that indicates that its predecessors have not marked it. It's it has no prime factors. So that is the moment when you say no prime factors means other than itself. It has got no prime factors. So you can directly say that we can actually have much minimized operations, and yet there it goes. This is actually the time complexity of sieve of Eratosthenes. This is the time complexity of sieve of Eratosthenes. If you apply n equal to 10 to the power 6, you will get something like 10 to the power 6 multiplied by log of 10 to the power 6 means log of 20, and log of 20, suppose you take base 2, what will you have? Over there also I took the base 2, so 10 to the power 6 multiplied by something like 4 or 5, whatever you take. Let us take 5, so it's less than equal to something like this. So this will get passed, right? Your test cases. But if you look at your initial approach, which was n root n, then that was not able to pass it. So this is actually the splendor, the magnificence of this algorithm, that it follows a very simple approach. And we discussed that if we start doing from just one prime number, how it is bettering our possibilities. We started from 137 or 137, we started from something like that. And we showed that by cancelling its multiples, we are able to reduce some possibilities. So here also it is basically the same thing. We have theoretically proved that if we do that same thing for all the prime numbers, then we can reduce the total number of computations. At least theoretically it turns out that asymptotically it is much lesser. So it is n log of log n, and it can be proved through some advanced mathematical techniques. You have Taylor series, you have many other techniques. So we'll be skipping that for now. Any other questions on this sieve of Eratosthenes, on the idea, on the implementation? Implementation, I'll be walking through the code. But before that, any other questions do you have? Okay. So let us look at the implementation slowly. So let's look at something like this. Or suppose it's Boolean primes. And this is of size n plus 1 basically. So up to n you require everything. So I've said n plus 1 तक हम देखते हैं. अब हम क्या कह सकते हैं यहाँ पर? हम ऐसा कुछ कह सकते हैं कि we have to move it, we can move it. By the way, प्राइम्स को पहले हम क्या कर सकते हैं? सारे प्राइम्स को हम इसको हम ट्रू से अपडेट कर सकते हैं. तो फर्स्ट we'll basically have all of them as true. So we can have this as the size, and then we will fill with true. So all values true. So in the beginning all values are prime, or we can say true, and then gradually we will say that we'll be iterating from the first number. For I equals to 2, I less than equal to n, I plus plus, we can do something like this. You can also optimize this upper limit, बट ठीक है कभी तो डिक्लेयर करना ही पड़ेगा. अगर एक एरे लिस्ट में स्टोर करना है तो ठीक है, इतना आप कर ही सकते हैं, नॉट अ बिग डील. यू कैन कीप लेस देन इक्वल, टाइम कम्प्लेक्सिटी को ज़्यादा फर्क नहीं पड़ेगा, बट यू कैन एक्चुअली ऑप्टिमाइज दिस, इसको आप रिड्यूस कर सकते हैं. सो वी कैन हैव समथिंग लाइक दिस का आई एन तक जाएगा एंड वी विल से दैट इफ primes of I is true, that means it is a prime number. What shall we say? कि इसके सारे मल्टीपल्स को विजिट करो, विजिट ऑल इट्स मल्टीपल्स, समथिंग लाइक फॉर j इक्वल्स टू 2 into I and j is less than equal to n and then j plus equals to I. So what will this ensure? That whatever values of j it is visiting, they are all multiples of I. Then what can we say? Primes j, they cannot be prime anymore. Since they are multiples of this, they cannot be prime anymore. Hence I'll be using this. And then I'll be saying, okay, you are done. The moment it is done, it's fine, and we can end it over here. This entire algorithm that I have shown here takes n log n. Okay? And now we can just return it. We can say now whatever number up to here you want to find, you can see whether that is prime or not. In order n, you can iterate through all the through the entire list, and you can find out which are the prime numbers. Okay. So this is the basic implementation, which is of order n log of log n. Any questions around this? Then we'll move on to the next part of our agenda. Why it is not n log n? The simple reason is that if we say that this particular operation, this inner for loop is going to run for all the values, if it is going to run for all the values, then we will say that then it would have risen to n log n. Then it would have been basically the harmonic series, n times the harmonic series. We could have shown that it is n times the nth harmonic number, which is n log n. But the moment we say that we are applying this if condition, and we know that only around, now this is an approximation, only around n by log n values up to n are primes. So we can say for all the primes, if you do it, we are only going to do for these operations. Only for these values we are going to do it. And we cannot apply the same thing over there, because that expression, nth harmonic number, is fixed only for the numbers taken from 1 up to n. We cannot suddenly put it. So there is a slightly different computation how we come to this value. But yeah, I hope that basically the idea is clear, that despite looking a bit expensive, why this helps finishing everything in quite a short time. I hope the idea is clear. Cool. Now suppose there are situations when we say that some numbers you have numbers up to 10 to the power 6, and there are Q queries. And we ask prime factorization. Every query we basically require the prime factorization of some AI, where AI is basically a number, and we say Q basically ranges to 10 to the power 5 and AI can range to 10 to the power 6. So every time, so we will perform basically Q queries, and this is just a sub problem. What I'm saying, it is, you will not find a question, you will rarely find a question directly asking you this. You will find this as a part of other problems. So for this you require something like some ideas like this, or maybe there are different questions. You might have heard the terms Euler-Toshan function. So over there we basically need to know the factors which are there and those things, or some questions related to Euler-Toshan function or Mobius function or similar functions. So some of these ideas actually help. So anyway, I want you to find the prime factorization, and also in the particular order, that is, if you talk about something like 24, I want you to print 2 into 2 into 2 into 3, and not in the other fashion like 2 3 2 2. You have to print in this manner and for all the numbers. So how can we use the sieve of Eratosthenes to make our problem simpler? If we don't use sieve, if we don't use the sieve of Eratosthenes, if we rely on our instance that okay, all these number I'm going to treat it independently, then what can we ensure? For this AI, how much time will be taken? To find the first prime factor, you have to travel up to square root of AI, right? Suppose you see that okay, I have done a primality test and now I know that this is not a prime number. If it is not a prime number, I might have to travel up to root over AI in order to find if it is divisible by that number or not. So then this is basically root AI and Q times root AI. Something like this it turns out to be. And also remember, you have found out the first factor using root AI. You yet don't know what will be the factorization of the next part. So next part, suppose you have some number, what can we say? Suppose you have something like 7 into 11 into something 13 or whatever we take. We can say that we have found out 7 in some time. Again, we have to find out now the factorization of the remaining thing. We have to divide this entire number by 7 and then we have to factorize this thing as well. So there are multiple steps which can actually take it beyond this. At least this much step is going to be taken. And we know that suppose like the constants are not exactly 1 and q can range up to 10 to the power 6. Suppose you say q will range up to 10 to the power 6, then it is absolutely infeasible. AI going up to 10 to the power 6, you can say now it is absolutely infeasible. You cannot have q root AI. So how can we optimize it? Think in terms of sieve of Eratosthenes. So you will actually find there have been Codeforces contests where this particular thing had been emphasized on. The time limits were kept very close to the optimal time which is taken, so that this n root n and these things cannot pass, because they are fractionally greater than n log n or n log n. That is the reason they were implemented like the time limit was assigned in that manner. So think how we can apply sieve of Eratosthenes to find out the prime factorization. There is also a related question which I was actually referring to, that is a number n a square free number? Is it a square free number? Square free number means all its prime factors have exponent 1. Square free number means, suppose a number you express that this has got some p1, p2 and p3. These are the prime numbers. You will say they are distinct prime numbers and they all have the exponent 1. They don't have the exponent 2. Sometimes the question is asked in this manner, that is it a square free number, and that is only a very small fraction of your code. You cannot spend more than log n time over there. In log n time you need to say whether that is a square free number or not. Maximum log n time. You can take log n, it will be better. But log n is a minimum necessity. Usually log n does not create problems when the optimal one is log n. Usually that does not create problems. But yeah, you need to find whether n is a square free number or not. But anyway, we'll discuss this later on. First, let us discuss this prime factorization of AI. How can we change, how can we adapt our observation of sieve of Eratosthenes to this requirement? It will be nice if you can come up with some ideas, and it will be like very interesting to keep it interactive. Else we can always have it one way, just talking about the convenience. Okay. Any ideas? It's there is a bit of a lag. That is the reason I'm waiting. Any ideas from your end? Whenever we mark a number, promising, impressive, what shall we do? Whenever we mark a number, we can append those. Okay. Appending means Appending means something like this. What will you append first of all? What are you going to append? So over here you're basically saying that whenever we visit j, we are going to append I, the value of I, to this primes of j, right? We are going to append I, right? We are sure it's a prime, that means you're talking about I, right? So for all the j which are multiples of I, we are going to take I and we are going to append it, right? Yeah, great. So yeah, there's a bit of a lag, please ignore that, but yeah, so that's exactly the case. We can append it, and now the question is, do we need to append all of them? If we append all of them, we can know that okay, a number can have how many prime factors? We know it can have log n prime factors. How log n? We can prove it. So number up to n can have at most log n prime factors, we know that. And but the value can rise up to root n. So the value will be maybe less than equal to root n, or some prime factor, at least some prime factor will be less than equal to root n, but number of values will be log n, so we can store all the prime factors right at that point of time. So yeah, good enough, we can use that directly. And then comes the question, do we require to store all the prime numbers? Can we say that without storing the prime numbers also we can make our task easier? Because the problem over here is that we are increasing the complexity of this algorithm. What is the complexity of this algorithm? It is n log n. Now think about it. If you apply all the values, what will you be essentially doing? Something like this. You will be saying that we will multiply this by some value which will be close to log n. Why? Because every j will now be associated with certain number of primes which can go up to log j. So it can go up to log j, right? There can be log j primes, and it won't be much less than log j prime, so there will be an increase in the complexity. Now think about it, you're quite close. Now think about it. Using this, yeah, we can do it. So what she is mentioning is we can have something like this. We have 2, 3, 4, 5, 6, 7, 8, 9, 10, suppose. And now we say 2 is going to mark this, so we are going to add 2. 2 is going to mark this, we are going to add 2. 2 is going to mark this, and 2 is going to mark this one as well. Now 5, when it will visit over here, it is going to mark this and it will say 5. So in 10 we have got this stored. So whenever we want the prime factorization of 10, we can actually read this and we can say 2 and 5 are the prime factors. But there is another thing as well. For 20 also we will have only these two, 2 and 5. So in order to get the exact prime factorization, we need to keep on dividing it, and we know how to do it. We can say take every prime factor and see up to where you can divide it. So we will say first, when it is 20, we'll be taking 2 and we will be reducing it to 10. Then we'll be again taking 2, we'll reduce it to 5, and then we'll be taking 5. So the prime factorization becomes 2 square into 5. So yes, if we have these values, we can do it in log of j time after this. But now the issue is that if you do this pre-processing, then your pre-processing is becoming a bit expensive. It is n log n multiplied by log n, which is a bit longer. If suppose I try to play a trick, I've given n slightly larger, it might make it fall below your beyond your time limit. Think about this, that q is much smaller than n. Q is much lesser than n. So I want to do that much work of working through all the prime numbers during the queries. I just want the starting point so that I don't need the root over AI computation. I just want to avoid that much. So what different can you think of from this stage? That we will be avoiding this, log j kind of a storage. I'm sorry, for all of them. We won't be adopting this log j storage for all of them unnecessarily. What can we do over here? The first reason why I want you to think more is this is not the traditional approach. The traditional approach is somewhere different, and but there is a reason behind that why people don't use it, because this is the problem with the time. You need a separate vector at each position. The vectors, again, they can grow long, they have their amortized time complexity, which takes the total time is less than equal to 2 times the size, something like that. So you can say that a bit of more computation than what is required, right? So what can you think of this? Can we say that we can just store one of these and that is sufficient? We will just store one of these for all of them, 2 and 2 over here. Okay, there is an important thing which I think I should mention. Over here, you basically won't have something like this, because when you're visiting it, you can always append it. So the problem will only come in terms of your space complexity. The space complexity will rise to n log n. So yeah, I take back the time constraint. Don't keep the time constraint in your mind. Why? Because since you're visiting it, only when you're visiting it to mark it, you are appending the value. So the number of appending is less than equal to the number of visiting. So yeah, forget it. The time won't be that much affected. But there is a space complexity, and secondly, it is not the traditional approach. So maybe we can try considering what the traditional approach is, which takes lesser space. We can say, yes, then look for 10. Yeah, okay, let's come to it. So we will do something like this. We have 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, up to suppose 24. We have up to 24. Now we will say that over here we'll be marking in this manner, that which is the first number crossing it. When I've crossed it, I will mark the first number or any of the numbers which are crossing it. Suppose I mark 2 over here. Now I'm marking maybe for 6 I can mark, maybe I'll be marking with 2 as well as with 3. So maybe 3 stays. Maybe 3 I'm marking later. Suppose I keep only the later marker. So over here I say that now 10. 10 is going to have the marker of 5. 12 is going to have the marker of 3. 24 is going to have the marker of 3. What can I say? That from 24, when I know I have to factorize 24, what will I say? That for 24 I'll see what is the thing over here. I'll see it as 3. So I'll just say that 3 into something, and I'll write 24 divided by 3 in my mind. So it is 8. I'll go to 8, and what will I say? In 8, 2 is going to place the marker. 2 is going to say that I am going to be over there. This is again the pre-computation. So we can see, yeah, keep the 2 over here, and then we will have 4 remaining. From this 4, what can we say? In 4 we have again got 2. So we can place another 2 over here, and this gets reduced to 2. And then we know that 2 is not marked, so it is not a prime number. So just add 2. So what do we get? This is the prime factorization in just the reverse manner. So it's just a different convention of writing. Hi Nikhil. So I hope the idea is clear, right? So for all the numbers, suppose in any order, all these numbers basically contain any of the prime factors which, any of the prime numbers which divide this number exactly. What can we see from there? That gradually, since all these numbers are associated with some or the other prime factors, we can take that prime factor, we can go to the just the quotient of dividing, after dividing by that, and then we can look at the next prime factorization. So it's like a recursion kind of an approach, where we say that for every number after the sieve of Eratosthenes, just by simple conversion in the sieve of Eratosthenes, we are able to get the first or the last or any particular prime factor for all these numbers. How are we getting it? We know that these numbers are going to be visited by all their prime factors, and hence we know that those prime factors are going to leave the mark. Any one of them are going to leave the sign that I have come over here. Whoever has visited last, suppose we are going to retain that sign as we are doing over here. So we can see, yeah, this is going to give me some kind of a prime factorization. Makes sense? Cool. So now what else can we say? Suppose this is absolutely random. Suppose you do it in a very random manner. Sometimes you store some greater prime factor, sometimes you store a lesser prime factor. Suppose you choose for 6, you make a decision that I'll be choosing, or maybe let us think of some example. 2 into 2 into 3, something like this. Yeah. So let's see how it is formed. Again, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We'll run the sieve of Eratosthenes, and what I'm saying is that 12 will contain the marker of, suppose 2. 6 will contain the marker of 3 and 2 will contain the marker of, or it will not contain any marker. The observation over here is that if we choose this prime factor first, we are getting 2 over here. When we go to the factor, that is when we divide this 12 by 2, we are going to 6. Now these are not invalid, these are valid. They all contain some of their prime factors, one of their prime factors. So we are taking into account this 3. We are saying that we'll now take the prime factor 3. So we are taking 3 and 6 divided by 3 will take us somewhere over here. We can say 2 is a prime number because it is unmarked. We'll have 2 over here. This is also a valid prime factorization, but not in the order that we want. And suppose we come back to this kind of a question where we want to find for Q queries whether a particular number is a square free number or not. What is square free number? That no prime factor is squared in that number. So what can we say from here? If the prime factors are arranged in a haphazard manner, same prime factors are not located one after the other, we have to store the prime numbers in order to find out which one is duplicated. So if we look at something like this, it is 2 into 3 into 2. We know that 2 is getting duplicated, but in order to find that this is a duplicate of some prime factor already visited by me, I have to store this somewhere. Unnecessarily, I have to entail some storage. However, if the prime factorization looks like this, I can just check whether this prime factor is matching to the previous prime factor. If it matches, that means it is a square free number. I can directly say that yes, it is a square free number. So you will actually find in many different applications. One I mentioned to you, it is the Mobius function. So in Mobius function, you will actually see the application of, now this slightly delving into some complex number theory. You'll actually see that square free numbers have got some significance. If it is a square free number, we assign a value 0, and if it is divisible by, I think, odd number of prime factors, then we have some value 1, otherwise minus 1, something like that. So from there, we actually say that in order to quickly check whether a number is square free or not, you can just roam through the factors one by one. You can check which is the immediate prime factor. You can divide by that, reach the number, find the immediate prime factor, and you can follow either of the approaches. So first thing, you can check that whenever something has been marked, the number now is not, the other factor is now not going to disturb it. It is not going to say that I am also contained behind you. It is going to say that take your, deem it as your lowest prime. So if every number stores its lowest prime factor, we can say we can obtain the prime factorization in this manner. Why? Because suppose we are dealing with, we got duplicated, So suppose we have something like this. Here's something like 2 cube into 3 square into 5 into 7 square. So what can we say? When we get this number, this particular number will have the marker of 2. And suppose this number is n, it will have a marker of 2. And hence we will say we will be adding 2 to our answer, and we will be going to n by 2. We'll be going to some n by 2, and this will also say that I am also having the factor of 2. We'll mark it over here, and we will say now go to n by 2 divided by 2. We'll go over there, and we will say that now this is also divisible by 2. We have again got the final 2. Now wherever we are going by n divided by 8, we will see that the factor is 3. Why? Because all of them are storing what is the lowest prime factor which divides them perfectly. So gradually we'll get these values. 3 square into, we'll basically get 3 over here, then 3 and then 5. So here we are going to get in the order. Make sense? So, and if you say that we are going to replace it always, that can be another possibility. You can definitely do it. And it's going to work fine as well. So what are we going to change in the algorithm, the approach? We are going to say that if it has not been marked, if it is, suppose we initialize everything by, suppose we keep it int and we initialize everything by -1. What can we say? Whenever we see that it is -1, we will deem that it is a prime number, and we'll visit all its multiples and we'll mark by that I. And then we are going to check that if that prime number has not been visited till now. So if primes j equals to -1, then we are going to do this. If primes j is equal to -1, then we are going to change it. Make sense? Then our entire algorithm will be computed, like it will be exactly the same. And now we can efficiently carry out the prime factorization. So now see how many steps are entailed in this. We can say that the computation is still the same. It is n log n. And what about the queries? Every query now comes to q times how much? Every number contains its prime factor. We can directly go over there. What will be the maximum number of terms? We have already discussed it. This can be maximum log to ai. Why so? Because we know that ai, if it has got some k terms, suppose it has got some k terms in its prime factorization, then ai is definitely going to be greater than or equal to 2 to the power k. Must be, right, because all the prime factors are at least 2. So from here we can find out that k is less than or equal to log of ai to the base 2. Make sense? So from here we can say that the number of prime factors is always less than or equal to 2 into log of ai to the base 2. What is the number of factors? Any idea? What is the number of factors of a number? Can be limited in terms of n. What is the number of factors of n? Maybe some asymptotic time complexity relation. Can we find out? Since we are discussing in this direction, actually order root n. Why using our same relations? That if there is any factor which is greater than root n, you will find its counterpart which is less than root n. So how many such counterparts are possible? Only 2 to root n or 1 to root n, suppose. So you have root n, up to root n. In 1 to root n, you basically have got maximum of root n numbers, and for all of them you can have a maximum of 1 counterpart after root n. So you'll definitely have 2 root n as the maximum number of factors. You can keep this in mind. These things often help in the contests when you need a quick approximation. Number of primes up to n, you might have known this. It is n by log of n. Okay, this is number of factors. Number of primes up to the number n. So that's it. So this Sieve of Eratosthenes, it is doing two different tasks for us. The first thing is it is finding out the primes. Second is for all the numbers, it is finding out the least prime number for that value. So you can directly apply in this kind of mathematical questions and wherever it is required, right? So the prime factorization won't be a burden for you. That part you can implement very smoothly. The rest of the things will happen automatically, right? So any questions associated to the concepts that we discussed today? I think we are nearing to our time of completion. It's a 1 hour session. Let me quickly tell you meanwhile about the batches which are being covered at Unacademy. You can ask me any questions if you have. So there you go. These are the 3 batches which are being covered. Mahayuddha is the advanced batch that I am conducting now. 2-month master course on advanced programming topics. In Eklavya 2.0, you have basically the topics that start from beginners and go up to the advanced level. 8 months course. Brahmastra is only for college and off-campus placements. All have started on 6th of July, and all of them provide you a structured learning path through one subscription. It is like a Netflix model. You can attain unlimited access to all batches and courses, and yeah, you'll have the best coders of India's educators. So in Mahayuddha batch, which I am covering, basically these are the topics. You have advanced mathematics, you have advanced dynamic programming, segment trees, advanced concepts of graph theory, mixed problem solving. Then in the Eklavya batch structure, you have the initial programming topics, intermediate topics on sorting and searching and associating. The basic data structures contain all your stacks, linked list, queues which are asked. You have greedy algorithms with classical problem solving. You have square root decomposition, number theory and interview questions, recursion and dynamic programming, graph algorithm with extensive problem solving. In Brahmastra, you have only the things which are pertinent to interviews, which are asked in the interview. These are the advanced things: string algorithms, advanced dynamic programming, and graph algorithms. And these are the old list of educators. Many have been added. You have live interactive classes, practice relevant problems at courtship, doubt support, and these are your educators. You can have a look at their profiles. They have had great involvements. You can learn a lot by interacting with them. And then this is the pricing. 1 month you basically need to pay 6,000. 12 months you need to pay 33,000. It increases downwards the discounts, and irrespective of all these discounted prices, you can get an additional 10% discount if you use my referral code Saptarshi 1729. If you use this referral code, you will get an additional 10% off on these prices. Make sense? So that's it. Any questions pertaining to today's session? If you have any questions, you can ask me right now. So if you are into computer programming, you can maintain templates on these small concepts. You can actually make a template on this factors version of it. So here you store the first prime factor for every number. If it is -1, it gets interpreted as a prime number. You can use this something like this as a template. You can find my template on Codeforces, which I've been using. And it is also interesting. You can also change this. I actually asked this as a question. We can also change this. If you have to find out up to n, we can conduct this only up to root n. So see, above root n, whichever numbers are there, in order for those numbers to be composite, what do we need? That up to root n, some prime factor should be there, right? So we can say up to root n. If we do this, then only it is fine. The problem is, it will be fine. It can be totally fine if you do up to root n. Make sense? You can calculate up to n. You can also calculate up to root n. It is perfectly fine. But this one cannot be decreased. For this one, you cannot decrease it. You need to go up to n. Why? Because you have to visit all the multiples up to n in order to indicate whether they are prime, whether they are composite. Sorry, or not. Right. This one is fixed. You have to give up to n, but this can go up to root n. Totally fine. Cool then. If no questions, we can. I'm sorry, I missed the message. But anyway, if you have any questions, you can type down. I'll wait for another minute and then we'll close the session. Cool then. Take care. Keep coding. Bye. Have a nice day. Have a nice evening.